This will be a short video that will walk you through the other type of electrolysis problem. This next example is the opposite approach of the example that we just saw. The question here, how long? So of course we're looking for an element of time. And usually you're looking for minutes. Usually that is the scale of time that we're trying to get a reaction to work for us. It would be great if it was in a matter of seconds, but realistically, usually these reactions happen over a span of minutes. How long must a current of 5 amps, so we automatically know 5 coulombs per second, must be applied to a solution of silver +1 to produce 10.5 grams of silver metal. So the reaction that we are doing is supplying a current and reducing, for every 1 silver ion, it needs 1 electron, and creating silver metal. All right, so the question is, how long will this take? We are trying to plate out 10.5 grams of silver. I would go right to moles so that we can get into Faraday and so on with our amperage. Silver is 107.87 grams in every 1 mole of silver. And to be most proper, we know that we are plating solid silver out, but our solution involves the silver +1 ion. So I'm just going to officially translate to be in terms of my ion. And I know that every 1 mole of silver ion will require the addition of 1 mole of electron. And 1 mole of electron is 96,485 coulombs of charge. Okay, so far that's going to give me coulomb. Now I know that I'm applying an amperage of 5 coulombs for every 1 second, and if I stop here, I'd be given seconds as my answer, but usually we're calculating to minute. So let me just check my work. I've canceled mass of silver, gotten into moles of silver, gotten into the ion, gotten in terms of moles that I'll need to reduce all of that ion, used the Faraday relationship to be able to get into coulombs, because here is my element of time, which is transferred in terms of amps. So 5 coulombs per second, and then getting us to minutes, and with sig figs, this will take 31.3 minutes. So the other type of manipulation that we might see, given amps and getting time, we're going to start with the mass that we're shooting for, where the previous example ended with mass, started with time and amps. This is a great theoretical proposition. Suppose an electrolytic cell contained all of these ions. Excuse me. If the voltage is initially low and is gradually increased, in which order will the metals plate out? Well, we ultimately want to reduce all of these completely. So if we want to approach it through that analysis, what we need to get are the E values for each of these half reactions. And that will reveal to us the general tendency of E's for these to happen. So for this copper to be reduced, the EMF standard is 0.34 volts. For the silver, it is 0.80 volts. And for the zinc, it is -0.76 volts. The more positive, the greater the pull for electrons. The more positive, the greater the pull. Now we're not sure what else we're trying to accomplish within this solution, but we would just take the lead from these, and do we see that the silver ion has the greatest pull? So it would be the one that would pull strongest for electrons, and it would plate out first. So if we're, addressing it per ion, this would first, then our copper, then the zinc. Or if we want to say which, in terms of the neutral metals, would plate, silver, then copper, then zinc. So these can be used, again, to reveal kind of the ease of the reduction or the strength of pull. I'd like to just emphasize for a moment the electrolysis of water. That is, a standard thing that may show up in May. Now, in essence, what we're trying to do is decompose water, but it's not as simple as we'd like to write. What we need to perform the oxidation reduction here is it needs to be an acidic environment, and usually we're incorporating sulfuric acid because it's really water, being here and having hydrogen ions, because what we're doing with water is actually oxidizing to create O2, and it's actually the hydrogen ion, not water, the hydrogen ion that then creates the reduction and creates the hydrogen ion for us. So it's these reactions together that actually complete the electrolysis of water. I'll attach, actually, let me give us, there's a great website that, let's see, it's www.wainet.ne.jp. I'll attach it to our podcast page. It's swirl YUASA//ENG electrolysis _of_water.SWF. I think this does a brilliant job, really step by step leading us through and being able to visualize what's happening with the electrolysis of water. But I'll attach this site directly to the podcasting page. The other thing that I wanted to just bring to your attention are past AP Chem exam questions. Just make sure we're seeing this okay. So you can walk yourself through what you may be asked to do with this information. This is from 92. If you want to pause and take a look at what the question is asking, and then I've shown all my work. So this problem wonderfully asks about the Nernst equation, asks to say if it is spontaneous or not, asks you to balance your reaction and get the E naught of your cell, and you know how much they love to ask you for molar mass. And so given amperage, you're doing some electrolysis, can you determine the molar mass of your substance? So if you want to look at anything, I would definitely look at this first part of the problem and then how I did my work to get and identify it was cadmium. Please pause for a moment and take a look at my work. I'd also like you to take a look at, this is from 1998, and this is more of a theoretical approach. You do have to get the E naught of your cell, but you're asked, whenever you add additional things to the battery, what would you predict would happen to the voltage? So if you could please pause, take a look at this, really think through, analyze my answers, and these two problems bring together and present you anything that you would have to answer about electrochemistry. I think this chapter is just a lot of fun. It's a shame that we have such little time and really are asked to just master such little information from this. Be sure that you can draw a voltaic, a galvanic cell. Make sure that you can choose which would be the oxidation reduction, that you can do the line notation, that you can apply the Nernst equation, that we understand the role of cell concentration on cell voltage, that you can do the dimensional analysis for electrolysis, and that you understand the theory of electrolysis as well as can master these kind of problems that might come your way in May. Best of luck with electrochemistry.